So, why are we interested in periods and Hodge structures? Well, one of the key reasons is that they're very useful for the parametrization of algebraic varieties. In this video, we're gonna look at some examples in the case of dimension 1, and we'll discuss the story about the higher dimensional cases in later videos. So a non-singular complex variety of dimension 1 is just a Riemann surface. And it turns out that a Riemann surface is uniquely determined by its periods. So let's look at the story first in the case of genus 1, because elliptic curves are just so popular. Let's see what we mean by a Riemann surface is uniquely determined by its periods. A Riemann surface of genus 1 is going to be an elliptic curve. We can think of it as a projectivization of an affine curve like this. Well, they are called elliptic curves because they arise from the computation of the arc length of ellipses. And that involves computing these integrals called abelian integrals. So here, y is an algebraic function of I. For example, let x and y have this relation so that x, y lie in this elliptic curve. Now, this integral is only going to be defined up to a linear combination of some complex number, two complex number, v1 and v2. Integer linear combination, I mean. So these integer linear combinations span a lattice inside C called the period lattice. This quotient then is a torus, so it's also an abelian variety, and the miracle is that this turns out to be isomorphic to E. That's what we mean by saying that the period determines the Riemann surface. This isomorphism is given by the Weierstrass P function. So this Riemann surface, this elliptic curve, is isomorphic to C mod R by its period lattice. Now all of this sounds a bit too magical because it's a bit too concrete, so we don't see the gist of it. So now let's look at it a bit more abstractly to see the structure. So we want to think of this integral as an integral of a form which generates the space of differential one form, holomorphic differential one form on the elliptic curve E. This integral, though, is not well defined because there are many paths that we could take from P0 to P1. If we integrate over this path, we might get a different integral than integrating over this path. Now, the difference of these two integrals is just the integral over around this loop. Now, this gamma is a loop. And actually, we can view this as a cycle. If this region is filled in, then this integral is trivial, since omega is holomorphic. So this integral is only defined up to the homology class of gamma. So even though this integral is not well defined as a complex number, it's well defined up to its value over cycles, the integral over cycles. Now these integral over homology classes, these are called periods. We claim that this actually forms a lattice inside C, so let's see why. Alright, so what is this homology group? Well, an elliptic curve is a torus, so it's isomorphic to S1 times S1. So this homology group is going to be generated by two loops, two elements. Let's call these generators gamma 1 and gamma 2. Now then every cycle gamma can be written as a linear combination of gamma 1 and gamma 2 with integer coefficient, right? But then this integral itself can be written as a linear combination of these two basic integrals. So this whole group of periods is generated over Z by these two basic integrals. In other words, it is a lattice inside C. That's why we call this the period lattice. So what's the isomorphism from C to this quotient? Well, we fix the point P0, and then every point P of the elliptic curve is sent to this integral. This gives us an isomorphism between the elliptic curve and the torus obtained by quotienting out by the period lattice, and that's why the period determines this Riemann surface of genus 1.